Welcome to the 13th lecture on module 1 on the course title Risk and Reliability of Offshore Structures. We are talking about lectures on module 1, which is focusing on probability theory and plausible reasoning. Today we will discuss about lecture 13, which is focusing on modeling of environmental loads. In the last lecture, we discussed about a variety of classification of loads, which is permanent loads or pre-class loads, L-class loads, environmental loads, deformation loads and accidental loads. These are all different class of loads. We already said, though some of the class of loads which can be computed accurately that can act on a given system, however, there are some degree of uncertainties associated in computing all class of loads. So, the uncertainties associated with estimation of class of loads can be handled or let us say addressed using characteristic value as recommended by the design codes. When you talk about the characteristic value of these kind of loads, researchers already said that one should go for the maximum value, so that uncertainty associated with these kind of variables which are input for the reliability analysis can be handled in a nice manner, so that probability of failure resulting from exceedance of these loads or variables will also be estimated fairly to a high degree of accuracy. So, environmental loads that act on offshore structures can be classified as P class, L class, D class, E class and A class, as you see here. So, there are different uncertainties associated with them. Let us see what are those factors which lead to these uncertainties, why we cannot compute these class of loads accurately. So, the factors associated with the uncertainties. Let us talk about this. Firstly, variability within material quality with respect to the strength and other engineering properties like modes of elasticity, area of cross section is one important variable. So, one important variable is the variability of material strength and engineering properties. Within the material quality. So, that is one uncertainty. Secondly, there can be variabilities in geometric properties of the components. So, variability in geometric properties of the components of the system or, to be very precise, we can say members of the structure. Which arise during the fabrication process. We know welding is one such process which induces hot spot stresses. So, interestingly, these variations can also be one of the reasons which result in uncertainties which cause the or which prevent the accurate estimate of different class of loads. The next point which contributes to uncertainty is one which arises from the change of load with respect to the C state. So, change of loads with respect to C states and operational conditions. That is another variation we have. The next one comes from the idealization of real structure into a model for analysis. For doing analytical or numerical studies, we idealize the real structure into a mathematical model. So, idealization of the real structure into mathematical model or numeric model for analysis. That is another major issue where we come across uncertainties. The next one can be which arise from the numerical and analytical computations itself. Errors that arise from numerical and analytical computation. The next important item which contributes as a factor for uncertainty is quality of workmanship. And lastly and most importantly, there is a degradation of strength I should say both the member and the structure due to aging effect, corrosion, etc. Now, the question comes, there are many factors listed on the blackboard here which contribute to uncertainties or presence of uncertainty in estimating the load class or input data which is necessary for reliability analysis. There is one more main issue which we have to again focus, based on which the environmental loads or the E-class loads are actually defined as a given input to the system. This is what we call as return period. Let us talk about return period for a few minutes. Environmental loads are associated with one of the main uncertainty that arise from its reoccurrence with a similar magnitude within the service life of the structure. So, we are talking about a major issue here. The major issue is reoccurrence of the load with the same, or to be very precise, similar magnitude. Within the service life of the structure. Offshore structures are very sensitive to this data because this is very vital in assigning the design loads to the given system. So, it is very vital, you have to specify this very clearly because this will govern the assignment of design loads to the given system, especially in analysis and design of offshore structures. Therefore, one is bothered about a combination of different events. As I said in the previous lecture, we are talking about different class of environmental loads, may be arising from waves, which arise from wind, which arise from earthquake, etc. All these events may be defined by different phenomena, either by nature or by man-made disasters. Obviously, the reoccurrence of a specific magnitude of interest within the service period of the structure for that of a wave or wind or earthquake may not be same. If I say RT is the return period, let us say, of earthquake, it may not be same as that of return period of the wave, it may not be same as that of return period of the wind. But unfortunately, we have to realize that environmental load or E-class load, what you see in offshore structures, which is one of the important input for reliability analysis, is a combination of these kinds of forces. We do not study only wave loads or only wind load or only earthquake loads, because in nature they are all present in a combined form. It means you cannot have an offshore structure's existence without the presence of wave and wind. You rather should design an offshore structure as an inherent system which can sustain design basis earthquake. That is a design guideline given by many international codes. Therefore, one cannot think about these events in isolation. So, I have to now look for what is called mean return period. Mean return period is the expected value or the expected number of years between which seasonal maximum is likely to occur. Is the expected number of years between which a given seasonal maximum is likely to occur. So, the keyword may be the expected, so it is a guess, maximum within the service period is likely to occur, there is a likelihood. Say for example, if the return period is 50 years, say for example, if return period is 50 years, what does it physically mean? It means that the characteristic load why I am saying characteristic? The moment I use characteristic, I am covering the uncertainty in estimating this load. So, the characteristic load is expected to occur only once in 50 years. So, one can have a question as a designer that the service life of my offshore structure is only, let us say, 25 years. Then why should I bother about an event which is going to occur only once in 50 years, because this period is much longer or larger than the atomic design period of the structure? Ladies and gentlemen, it is very important to realize that 50th year where this event is going to reoccur can be the current year where your structure is designed. So, we are not sure when this will reoccur, but we are only sure that it will reoccur only once in that period. But we really do not know which is that year exactly will occur. Will it fall within the service period of the structure? We do not know. Now, instead of looking at the return period, let us talk about the inverse of this. That is more interesting. Let us talk about the inverse of the return period. Inverse of return period is the probability that the extreme value, why I am saying extreme value? Because you please see the definition of return period, it is the seasonal maximum. So, I can always use an equivalent word extreme. So, inverse of the return period will be the probability that the extreme value of the event will be exceeded in any 1 year. This is the clue. This is where we are important, we are interested. Let us say, for example, if the return period of any event is 100 years, one can say why it is so high. This is very classical example because this is a very common case of wind loads as advocated by many design codes. So, if I know the return period of a wind load as an event which is 100 years, then I can say that the probability that the characteristic load will be exceeded in any 1 year will be equal to 1 by 100, which is 0.01. So, what does it mean? It means that there is a probability that the maximum or the extreme value of that event will be exceeded in any 1 year is only about 1%, that is 0.01. So, 99% there is a guarantee that this extreme value event, what you have considered as a return period with that of the wind load event, will not exceed in any 1 year of your design. You understand? Now, we are trying to connect the probabilistic exceedance of this value with that of its return period. But the designer is not happy with this. I will come to know, or I will come to explain you what actually the designer wants. As a designer, one may not be interested to know the reoccurrence of any event with its extreme value. One is not interested to know the reoccurrence of any event with its extreme value. Then what is he interested in? He is interested to know what is the probability that the design load will be exceeded. During the lifetime of the structure. So, he will be interested to know what is the probability that this will be exceeded during the lifetime of the structure. Now, how to estimate this? Now, since 1 by R is the probability that the characteristic load will be exceeded in 1 year, one minus 1 by R will be the probability that it will not exceed in any 1 year. Let us say the life of the structure is denoted by letter n. Let n denotes lifetime of the structure. So, the probability that the extreme event will not be exceeded during those n years, because that is the interest of the designer, will be the designer's interest. So, this can be easily given by 1 minus 1 by R to the power n. Therefore, probability that characteristic load to be exceeded at least once in the lifetime of the structure is given by P n 1 minus 1 by R, because you have already seen this value is non-exceedance. But now I am looking for a probability of exceedance. So, 1 minus 1 by R to the power n. So, return period can be connected to probability of exceedance and further connected to the lifetime of the structure using this equation, which we call equation 1. Let us say return period of a structure, for which an event is designed, is 50 years of any event. So, the characteristic load whose return period is 50 is known to us, and let the lifetime of the structure be 20 years, which is very common in case of offshore structures, because the oil reserve which is used for exploration does not be consistent beyond a period of about 20-25 years. So, therefore, we say the service life of an offshore platform can be approximately equal to about 20 years. So, what is the designer's interest? The designer's interest is probability that this design load, whose characteristic value is known, is exceeded, because you should design it for exceedance at least once during the 20 years. Why 20 years? Because the service level structure is given by P20 1 minus 1 by 50 raised to the power 20. If you can calculate this, it becomes 0.33. So, ladies and gentlemen, look at this particular example, an event whose characteristic value will not exceed or will not reoccur, or it will occur only once in 50 years of the same magnitude. Even though a service period of the structure is much lower than this, the probability of this value being exceeded during a service life is about 33%. So, therefore, you have to address this kind of uncertainty very carefully as an input data for reliability analysis. If you are not able to account for this uncertainty in the input variable for reliability analysis of offshore structures, your probability of failure of the given structure under the given load combination system will not be accurate. So, you may not be happy knowing that a event whose return period is far away from that of a lifetime structure, because there is always a probability of exceedance of this at least once within 20 years is about very high number. So, one has to account for this uncertainty in the analysis for sure when you especially do estimate of probability of failure. Therefore, it is clear from this illustrated example that there is a chance that the design load exceedance from its characteristic value at least by 33% once within the lifetime of the structure. As a designer, this is quite important as this percentage is phenomenally high for a reasonable estimate of the cited example. Therefore, how they are accounted in the design? People use what is called safety factors. So, this is addressed, or this complexity is addressed by using what we call safety factors in the design. However, different codes address this safety factor by using a term called partial safety factor. Why it is called partial? Because this does not account for all uncertainties which are associated with this safety factor, because even calibrating safety factor itself has got mathematical uncertainties. So, you can look at this as the reference Srinivas and Chandrasekharan. My own book on advanced marine structures, reference indicated as 2015 C in the NPTEL website. You can also look at Marshall 1976. You can also look at Tasman et al. 2009. So, there are various researchers who have illustrated why the safety factors still cannot account for all uncertainties accurately. But here we leave a note saying that it is very alarming that the exceedance of probability of any specific event is very high in number for a given chosen example, which is very common application for offshore structures. Therefore, one should account for this uncertainty by using what is called safety factor in the design, which is advocated by many international codes for design of offshore structures. Having said this, let us talk about one more important characteristic, which is estimate of distribution parameters. So, we already said for doing reliability analysis, you need to have a data which we call ensemble or the input value. The input value generally can be a random number or random generated simulations numbers. They should follow or they should obey or they should closely adhere to a specific kind of distribution whose probability density function is known to us, because it becomes easy for me to estimate the distribution parameters. So, let us talk about estimate of distribution parameters. Probability distributions are vital part of statistics. There are very few practical applications of this. Let us say probability distribution has few vital applications. One, they are required to compute the confidence interval for parameters. To compute the confidence interval for parameters. Two, they are also required to calculate the critical regions for hypothesis test. For a univariate data, it is often useful to determine a reasonable distribution model for the data, whereas the statistical intervals and hypothesis tests are often based on specific assumptions of the type of distribution that shall follow. So, therefore, before computing an interval or the test based on this assumption, one should verify the justification of the assumption for the given data set. This does not mean that the distribution needs to be the best fitting distribution for the chosen or for the given data, but it is very important to know an adequate enough models should be assumed so that the statistical technique yields valid conclusions. For example, if a set of data follows a normal distribution, if your distribution assumed in the analysis does not obey a normal distribution, the conclusions derived from the analysis may not be completely valid. It is therefore important to use the simulation studies with random numbers that are generated using a specific probability distribution. There are various methods, both numerical and graphical, for estimating the parameters of a given probability distribution. Let us see quickly what are they. So, we are now talking about methods which are useful for estimating the parameters of a probability distribution. Method of moments, maximum likelihood functions, least squares, probability plots. Let us quickly see one by one. Let us talk about method of moments. Method of moments equates the sample moments to that of the parameter estimates. It tries to equate the sample moments to that of the parameter estimates. It has got a primary advantage. The primary advantage is the method is very simple. Whereas the main disadvantages, they are not often known. Even they are known, they do not qualify to have the desirable properties of maximum likelihood and the least square estimators. Therefore, the primary use of method of moments is only useful for initial approximation. So, this can be used only for initial approximations to estimate the maximum likelihood and least squares. That is what many researchers has commented with it 1990. When then 2004, Wishing et al. 2006. Let us talk about the next method, maximum likelihood. Maximum likelihood estimate begins with the likelihood function of the sample data. It starts with the function of the sample data. Likelihood of set of data is nothing but the probability of obtaining that particular set of data from a given or a chosen probability model. So, what is the likelihood that the chosen data will follow a standard pre-assumed probability model? That is the likelihood function. This contains unknown parameters whose values that maximize the sample likelihood, which are known as maximum likelihood estimates. So, one has got to calculate maximum likelihood estimates, which are nothing but the maximize the sample likelihood to follow a pre-assumed distribution. Maximum likelihood provides a consistent approach. So, that is an advantage. It has a consistent approach to the parameter estimation problem, which enables it use for a large variety of estimation simulations. Therefore, maximum likelihood method is desirable mathematically and is optimally better. They show minimum unbiased variance estimates for large sample size. Unbiased variance is minimum for large sample size. Now, we are considering a very large number of random samples to replace the original sample population. The average value will match closely to that of the population value. That is an advantage when you use the likelihood method. As this will show a minimum variance, it expresses the narrowest confidence interval of all estimates of the type. And the next advantage is they generally follow the normal distribution. Therefore, sample variance can be used to generate confidence bounds and hypothesis tests for the parameters. Several popular statistical software packages provide excellent algorithms for estimating maximum likelihood estimates for many of the commonly used distributions. That is an advantage. Therefore, this helps ready use of estimating MLE for a given probability distribution. This helps to mitigate the computational complexity for finding out the MLEs, but there are some disadvantages. Likelihood equations are case specific for a given distribution. So, they cannot be generalized. Secondly, the mathematics which is being used is often non-trivial. Is often non-trivial, particularly if confidence intervals for the parameters are desired. Except for a few cases where the maximum likelihood estimates are in fact simple, in general best to rely on high quality statistical software are being used to estimate MLEs. Fortunately, high quality maximum likelihood softwares are available and they are being commonly used, but maximum likelihood estimates can be heavily biased if the sample size is small. If the sample size is small, the MLE can be heavily biased. It is suitable for large samples. They are also highly sensitive to the choice of the starting value. So, sensitive to starting values. The third one is least squares and the fourth one could be the probability plots. We will talk about this in the next lecture. We will try to compare them and see how they can be useful in computing the sampling distribution. So, I urge that you should follow the reference materials given in the website, read the papers in parallel and also the textbooks advocated to you in the NPTEL website of the specific course. Try to develop your capacity building in parallel to the classroom lectures. Anything you want to share or discuss, kindly post it in the website of NPTEL so that your doubts can be answered then and there. Thank you very much. See you in the next class.